sounds good.
Hello and welcome back. Sorry to start a little bit late here. We were having some AV issues, and on that note, the presenters prepared their slides on Mac computers and are now presenting on a Windows computer. So please bear with any kind of formatting or animation issues that may come up. Also, we've been instructed when you're asking questions, please do come up to the microphone. We are capturing this on video. So please do come up to the microphone so your voice will also be captured. And when you do, introduce yourself, including your institution. Okay, so without further ado, let's start this first session of HotMobile 2019. The topic is video analytics. And for our first speaker, we have Shilpa Anna George. She's a first-year PhD student in the computer science department at CMU. Her research areas include computer vision, mobile, and edge computing. She's working on problems involving video analytics and reducing human efforts in building large-scale data sets. Today, she's going to present towards drone-sourced live video analytics for the construction industry. Shilpa.
Good morning. Thank you for the introduction. I'm Shilpa George, and I'll be presenting our work towards drone-sourced live video analytics for the construction industry. This is a joint work with Junju Wang, Mihir Bala, Thomas Eisler, Babu, and my advisor, Professor Satya. So first, let's take a look at the construction industry. By the year 2022, the US construction industry is valued to be over $1.8 trillion. However, this industry remains one of the least digitized sector and has seen very little improvement for the past 2 decades. For example, let's take a look at how the task of inspection is conducted. So this entails that the client or the architect walks through the construction site and inspects whether the construction on site complies to the architectural drawing. And most of the times, these architects view the drawing as a PDF on their mobile phone or the tablet. Or in worst case, they have a hard copy of the printout. So you can imagine in a large-scale project how tedious this can be. We can definitely do better than this. And one way to do this is to use drones in construction. So drones provide a bird-eye view of the construction site, and they help to cover a large area in little time. I have listed some of the current use cases of drones in the construction industry. One of the interesting cases is drones are deployed periodically to capture time-lapse video where they capture the progress of the construction site. But if you notice, all these use cases mentioned actually does processing post-flight. That is, the data captured by the drone is offloaded to a cloud where it is used to create a 3D mesh file or a topographic map. What we are interested in is the potential of live video analytics of drones in construction. And we take the case of registration as the use case. What do I mean by registration? Given a drone view, we want to accurately find its position on an engineering drawing. So you can imagine in our user scenario, we want the architect either on the site or at a remote location to see the annotations of the virtual drawings on the virtual drawing of the drone flight in real time. So the benefits of live analytics include real-time actuation based on the current observation. So if the architect observes some abnormality in the construction, he can actually ask an operator to fly the drone for a closer inspection. And this allows prompt detection of trouble spots and hence improves productivity. You can also view this as an inverted form of augmented reality. In classical AR, we actually annotate the real world with some virtual observation, But here in our case, we are annotating a virtual world where it is the engineering drawing, and we are annotating it with the real world observation. So what are some of the challenges in realizing this vision of live analytics on drones in construction? One is a small, inexpensive drone does not have sufficient computing power to perform or sustain live video analytics. So we overcome this by offloading the computation to an edge computing infrastructure or a cloudlet with substantial computing resources. Another challenge is the architects we collaborated with had their designs using a software named Autodesk Revit, which is implemented to run only on Windows operating system. Now the drones run in Linux or has embedded RTOS and will not be able to host these software. So we leverage the virtualization capability of a cloudlet to execute these Windows-based software. So this shows a demo of our edge-based prototype. In the inset, you can see the drone, what the drone captures in real time. And we are annotating on the virtual drawing using the red bounding box shows what the drone is seeing in real time. So to describe the case study setup, we did our experiments on CMU Tepper building. This is a newly constructed building that completed in September 2018. From the architectural firm, we obtained the engineering plans, which included both a 3D model and 2D elevation plans. The industry standard requires that these engineering drawings be within a quarter or 0.6 centimeter of the actual construction. So this bounds the accuracy precision that we are aiming for. And for the drone, we actually use a DJI Phantom 4 Pro, which has a mounted camera and a variety of sensors. Now I'll walk you through the system architecture. First, we have an operator who controls the drone, and the drone sends video as well as sensor data through a wireless channel. And this data is transmitted from the controller to a ground-based cloudlet, where we have two virtual machines instantiated. In the first virtual machine, we run a computer vision localization algorithm, which localizes the drone's view on the engineering drawing. And this result is passed on to the second VM, which is an Autodesk VM that's running Windows. So in this, the user can see the result of the localization of drone source location on the Revit files. So one question that can be asked is, if the model is calibrated according to the world coordinate, why can't you just use built-in position sensors? So we explored this, and we measured what is the horizontal and vertical accuracy when using GPS sensors. So what can be noted is the required accuracy that we are aiming for is 0.6 centimeter, and none of these come anywhere close to that. So we explored how can we use vision in this, and we use existing computer vision techniques such as feature matching to obtain localization. So one requirement for SIFT feature matching is the two images being compared should have similar visual features. But if you notice what the drone is seeing, that the query images look very different from the architectural drawing. So then how do you map? For this, we introduced an intermediate step by introducing something called reference images. Now, what we do is we captured wide-angle images of the exterior of the building at different locations, and we manually registered these to the virtual drawing. These images in the database are actually indexed using the SIFT features. So now, instead of directly mapping the query to the virtual drawing, we'll be mapping it to these reference images, which are already mapped to the engineering drawing. So to go through this, if this is the query image that the drone is seeing, we first use the GPS to narrow down the search space. Then we retrieve the best matching image from the database, which has the most number of matching features. Then we find the feature correspondences between these two images and map the query frame to the reference image. So the bounding box in red shows the location of the query frame with reference to the reference image. And then because we already know the mapping between the reference image and the engineering drawing, we can easily get the mapping of the query frame to the engineering drawing. Now to move on to the evaluation. Using a SIF matching, majority of the time we are able to get an accuracy of about 10 centimeter, and over 95% of the time we are able to localize within 20 centimeter. Along with accuracy, another parameter that's of importance is where should the compute be placed. So for a 720p image resolution, we ran it on 2 platforms. We had Intel Joule emulated drone platform, and we had a beefier cloudlet. So on the drone platform, we are getting a frame rate of about 1 frame per second. Whereas on the cloudlet, we see about a magnitude of improvement in the speed up. Now to consider some of the future works. So the reason we consider live registration is it is the first step to achieving many other applications such as live mapping and real-time error detection. So our work is just an initial step in this application space of live video analytics in construction. So there are a lot of improvements that can be had. One of the improvements is improving the accuracy and speed. As there is temporal consistency in the drone video, we can actually use tracking instead of doing frame-to-frame processing that we are doing in our method. And in our approach, we are actually registering the reference images to the engineering drawing manually, but you can actually use precisely placed fixed cameras to automate this process. Another interesting future direction would be to train a DNN to learn a mapping of the visual features from the architectural building to map it to the architectural drawings. In summary, though drones are used in construction, they are mainly done in offline processing. And live analytics enables actuation of the drones in real time based on the current observation. So to conclude, in our work, we use edge computing and vision techniques to perform live registration of drone views on virtual drawing. There is a rapid adoption of drones in construction industry, and the area of live video analytics is an interesting area to explore. Thank you.